Hi everyone, this is going to be a follow-up video to the original pre-lab lecture that I've already uploaded to YouTube. Usually when we do this lab in class, a great deal of time is dedicated to walking through all the Excel commands that you're going to need to process this data. So we're going to have to do it remotely, even though we'd usually do this in class together as an entire class. So ultimately what our goal is going to be is to fill in this chart here. And it's not going to cut it, at least for this lab, to do any of the calculations by hand. The majority of the points for this worksheet come from submitting your Excel worksheet to me and me checking to make sure your Excel commands are the proper commands. So you don't need to refill in all the numbers on this chart here on the worksheet because you'll be sending the Excel sheet to me separately. One thing that so our ultimate goal is to find Planck's constant in units of joule seconds. What we're going to see is we're going to have a series of colored LEDs, and we're going to have a series of voltage data that is associated to each of those LEDs, so the minimum amount of energy needed to turn them on. From that, we should be able to calculate Planck's constant from several different wavelengths of light. They should theoretically all be exactly the same because this is a universal constant, but we'll see. There'll be some error. There's always error associated with experimental data. We're also including infrared data. Humans can't see infrared. We typically refer to this as heat because what we feel as heat is usually, especially when it's radiant heat, is infrared photons. So humans can't see that, so I'll have to supply some of the extra data for you, like this wavelength here. It's too long to be seen by humans, but it's a particle of light, so we will be able to figure out Planck's constant from that as well. What I do need you to report is going to be the average and the standard deviation for the Planck's constants that we calculate, and that needs to be reported with correct sig fig. What I also want to do is clarify some of these questions in the pre-lab worksheet before we even get started. There's not a lot of them. I think there's only a total of, what, 6 or 7? 6 problems. They're pretty straightforward, but I just want to clarify some of them just because the wording in the past has left students sometimes confused. So part 2, after you've filled in your chart in Excel, you've reported an average Planck's constant with standard deviation. It's asking you to calculate the percent deviation of Planck's constant. So I don't believe we've done this calculation before in lab. You can find the equation, I believe it's on page 26 of the lab manual or somewhere about there. You can also Google this equation as well. It's pretty straightforward. Calculating the percent error, that's another thing you're all familiar with. Question 4 is asking if blue light or red light has a higher energy, and then to what wavelength do these colors correspond. So for a fully correct answer, you're going to need to link those wavelengths that are associated with red or blue light and then show why one of the two has a higher energy. So it's effectively linking wavelength to frequency to energy. Question 5, I don't know if I directly addressed this in the pre-lab lecture that I pre-recorded. If not, what I'm going to do is just do a quick overview about this dual nature of light. So a lot of the pre-lab lecture that I focused on was the wave nature of light, and that two particular properties, wavelength and then also frequency, or nu. Right? These are two properties that describe how a wave propagates. One is telling you the distance between the troughs, and then frequency is telling me how many of those peaks or troughs pass through a given point per second. And so this is our wave nature of light. So wave nature. This was what was discovered first. This is the Maxwell equations describe the behavior of light. So light is definitely a wave. So it is an electromagnetic wave. Light, and I did mention this in the pre-lab, but maybe I didn't elaborate enough, is also a particle. And that particle is called a photon. So particle of light. So just like an electron is a particle, except electrons have mass, light does not. This is still a particle of light. So light is behaving in two different ways, and actually depends on how you observe it. it can either behave as a wave or as a particle, and this is called particle-wave duality. All matter actually is both wave and particle, so electrons 100% are waves, they are also particles. You can calculate your own wavelength as well, but that's beyond this course. You'd use something called the de Broglie wavelength, but there's a definitive link between wave nature and particle nature. So effectively, I probably gave you the answer to this, but that's what we were speaking of in the particle-wave dual nature of light, so particle-wave duality. Part 6, this is usually a lot easier to see if we were in lab collecting the data, and it's kind of a vaguely worded question, so I'll help you out a little bit this time around. So it says most people prefer natural light from the sun as opposed to artificial light from a bulb. So how does light from the sun differ from fluorescent light bulb? So what effectively the question is asking, if you have sunlight coming in, the sun is generating all that light because it is just incredibly hot. And when things get hot, they glow. And so when you turn on an electric stove and you see it glow red, that's because anything that temperature will glow red. If you keep increasing the energy, you start to mix in other wavelengths, and it starts to appear white to humans because you're starting to see all the colors of the rainbow at once. And so that's where sunlight is coming from, right? It's just you have a massively hot object that's emitting light. And so it's going to emit in all frequencies. Not equally in all frequencies, but in all frequencies. Especially for humans, it matters because the majority of the light that the sun puts out is white light that we can see. So if we pass this sunlight through a prism, it will separate it literally into the rainbow. That's because sunlight has all frequencies of light. A fluorescent light, however, I'll call that F light. It looks like flight, right? You pass that through a prism, and what we'll see, it'll be discrete wavelengths. So I'll say discrete wavelengths. So basically, it's humans' attempt to approximate sunlight. So if you have an incandescent bulb, yeah, that's just hot, so it's going to actually produce, that's why it's a softer, whiter light. Fluorescent lighting, we're limited by physics and chemistry, and so only certain wavelengths can be given off when you pass electricity through a gas, and that's why you're seeing discrete wavelengths. So what is this question referring to? Let me back out, and we'll go back to, oops, that's not what I wanted. We come back to the worksheet, or at least the description of the worksheet that I sent out a couple of days ago. So what am I talking about? Fluorescent lighting passed through a prism, right? In this case, the prism is a handheld instrument. We call it a spectroscope. If we were doing this in lab, you guys would point this both at the sun and at the fluorescent lighting in the room, and you'd see something very similar to this. So what you're seeing here is fluorescent lighting. If you were looking at the sun, the entire thing would be filled up on the bottom with the rainbow. So, for us, we can see, at least in this particular example, there's 1, 2, 3, 4 discrete wavelengths of light. Blue, green, yellow, and red. And so we'll come back to this in a second, but this is going to be actually we can just do the, well, let me go in my order of my plan, then we'll come back. But we're going to be using this data, and I'll show you in a second how to write that data down. And we're going to couple it to voltage data that I sent you. So the voltage is going to tell us the minimum amount of energy needed to turn on the LED. And so effectively what that's telling us is the potential needed to push one electron through. So if one electron goes through, then it's going to light up. And that's basically the voltage threshold. So we can eventually convert this into joules. Right now it's in electron volts. So technically that should be E capital V for electron volts. So let me go back to our worksheet. Oh, not this one, but this one. Oh, was I in the right spot? Where did it go? Oh, this is what I wanted. So we'll ultimately be filling in this table. So you can already see where I'm going to need voltage. So we said we're going to get that information from the voltmeter. And we're also going to need wavelength. and then that's going to be coming from part A or from the spectroscope. So let me write that down. We have voltmeter, and technically that's part B, and then here we have our spectroscope, and that's technically from part A. So we're going to be combining those two bits of information to ultimately determine Planck's constant. That's our ultimate goal. So let's first get back to talking about how do I record the wavelength, and then we'll jump into doing the Excel part of this. So let's go back to this figure here. So how do I get wavelength information from this static picture? So a couple of things we need to pay attention to. We can see, I've already given you an example for blue light. So blue light is at 495 nanometers. And so the spectroscope itself is going to go from about 400 up to 750. This is the range in which humans can see visible light. And so we automatically know we're going to be in the order of magnitude of nanometers. This so happens to be what visible light falls into. So what we see here for blue, there's my blue light, and I'm reporting it as 495 nanometers. Well, if we take a look here, there's a 4. Oops, it's kind of hard writing on black. We have a 4. Each one of these tick marks is 10 nanometers, and we're going to do our best to approximate to 5 nanometers. So what I see here is the blue light is not quite 5. It's a little bit more than the 9th tick mark past 400, as past the 4. So that's why I'm going to write it down as 495 nanometers for my blue light. Give yourself 2 seconds to practice. I'll give you the answer in a few seconds, but I want you to either pause or wait to try and figure out what is the wavelength for this green light that we're seeing. So the way I would go about it, I would immediately see that I'm to the right of the 5, so I know, but I'm not as far as 6, so I'm definitely going to be in the range of 500 nanometers. The green light is a little bit less than 550, and to me it actually looks like it's right on the nose for 540 nanometers. So we're doing our best, if we can, to get down to plus or minus 5 nanometers. So some people might see things differently. That's totally fine. That's the reason why we're actually doing several different, using several different pieces of data to help average out any of those human errors. So that will be up to you. You'll need to fill in the wavelengths for green, yellow, and red. You'll also notice, if we switch to, I don't know if it's here, if we go back here, I've also given you the wavelength for infrared light. So now let's start to bring everything together. So what I have here, this is all the voltage data that was given to you in part B, and then here's some of that data that I gave you for wavelength. Like I said, it'll be up to you to use the spectroscope to fill in green, yellow, and red wavelength. Also, what you've seen is I've started to organize the data. So I've gone ahead and plugged in some of the data already, but a major component of this assignment is learning to organize and present your data. So when you get a job, we release you into the real world, and you got your nice fancy job, part of your job in almost all instances is going to be presenting data to someone else, and you're not always going to be there to explain exactly what you mean. So the best way to get around that is to organize your data very explicitly in a logical way, and that's what we're going to work on, and that's partly what you'll be graded on as well. So what you see here, I've already put in the voltage data. I've organized it. There's my voltage. I know exactly what unit it is, electron volts, and I have trial 1 and trial 2. For Excel, if you're going to be doing any math, you cannot have letters with the numbers. Excel will not understand that. That's why I have my units to the top. Other times, what you might be able to do, and I've done this myself, is to put the units right next to the number. Sometimes that's helpful. You choose how you want to present the data. I find it more helpful when you have a long string of numbers like this. We'll be doing a lot of calculations to have the units on top, so it gets a little less messy. So let's start off. The first thing we only need to calculate is average voltage, because we did 2 different tests. So for Excel, or this happened the last time I tried to record, as soon as I start typing in Excel, it restarts the countdown to start recording me, though the last test I did, it didn't seem to affect the outcome. So if things do get messed up, please let me know. So for doing the average voltage, right, we're not just going to add the two together and divide by 2. That's how would you do the average in the calculator, but we're not concerned with that. I know you can take averages. So what we're going to do here is we're going to tell Excel we're doing a command. How do I do that? I have to write the equal sign first. Now Excel can understand that this average is a command and not just the word average. So I have average, open parentheses, and then I highlight whatever cells I want to average. In this case, B3 and C3. Hit enter, we're good. This is something that students sometimes blows their mind, like, oh man, I can't believe why don't I use this more often? So I could retype this equation every single time. It's reasonable when I only have, 1, 2, 3, 4, 5 bits of data. What happens if you have 1,000, which is definitely reasonable. So to get this calculation to happen reoccur several times, what we do is you click on the cell, and you'll see here I have a filled-in square. Hover your mouse over it, and now it is a black cross. Click and drag down. It repeated that command every single time. So what we noticed here, because it said the average of B3 and C3, well, there's B3 and C3. When I pull this down, it now goes to B4 and C4. Pull it down again, B5 and C5. And so you can double check that with your what it's writing down. So we now have our average electron volts. So let's move on to average voltage, but now converting into joules. So what I'll need to find then is actually a conversion factor. So where are we going to find that? Well, we're going to find it in our lab manual. So we'll need to go through and then find our conversion factor. So what we can see here, if you haven't already found it already, there's my conversion factor. So it's the average voltage, well, it's a conversion between voltage to electron volts, to energy. So it's the amount of energy one electron would have if it's accelerated through a 1 volt potential. That's physics. We're not going to get deep into what that means, but right now, if we can use it as a conversion factor, we'll be in good shape. So as a conversion factor, right, I'll try to find some space to write, we can say 1.602176646, and all those numbers are known accurately. That's why we can include them. It's not rounded off or anything like that. That's how many joules one electron would have if it's accelerated through 1 volt, and that's what we represent as an electron volt. So still, it seems like I got a better stylus, but the screen mirroring program I'm using is not as accurate as I'd like, so I'll do my best to correct things. So that should be the number 1, right? 1 electron volt. And so we'll need to set up some sort of equation like this in Excel. So let's try that. Let me just write down real quick because I realized I don't have it written down. I need to write it down physically in front of me so I have that number. So 1 point. Yeah. First pencil I grab is dead, or pen. 1.602176646 times 10 to the negative 19th joules per electron volt. All right. Sorry you had to hear me talk that out. So let's get back into Excel. Again, I'm going to need to convert electron volts to volts. I cannot write conversion factors in like I normally would, but I usually have my students do this, and actually the reason we do it is because that's what most people do in real life. You're not going to try to write out the equation in your first attempt by typing it into Excel. You'll find out that's going to be too much of a pain. So what we're going to do is we're going to start with the 1.63 electron volts that we're given, and we're just going to do some dimensional analysis. So I can see if I have 1.63 electron volts for red, I know for every 1 electron volts, that would be equivalent to the 1.6021. I'm going to stop at 76. Well, we can do the whole thing. 46 times 10 to the negative 19th joules. And so what we can see, sure I don't mess up, my units for electron volts cancel out, and I'm left with the units I want, which is joules, which is exactly where we're going with this. So, how do I convert that? I probably should have left that on the screen, see if I can get it back up. I can't, good. we need to convert all of this, and sorry it keeps popping up with that press escape stuff, right? We need to convert what I have written on the screen into a written Excel command. So let's do that. It seems like it's going to fight with me, so I'm going to have to erase it. But the way we do that, we can say equals, oops, I need to get out of the writing tool, equals, because we're doing a command. If we remember what we were setting up on our dimensional analysis, and I recommend going back and maybe writing it down by hand before moving on with this video, this is my 1.63. I could type that number in, but what if happens if I found out later I messed up my calculations in, say, any preceding column? Well, then I'd have to go through and change everything by hand. What I've done instead now is link this, what's happening here in this column, to here. How'd I do that? Instead of typing 1.63, I'll just click on the number. We can see that it's linked. So if I changed it here, that number changes. If I changed it all the way over here, the number changes. So it's, oops, linking. Uh-oh, I didn't screw it up too bad. There we go. It's linking all the cells together, so if I make a mistake, I can easily fix it. But that wasn't my goal, was not to just reduplicate that number. It was to take that number and then multiply it by the 1.602176646 times 10, oops. So I can't just write x. So this is what most people would try to do, write the x in there, and Excel will get completely confused. Multiplication in Excel is going to be the asterisk. So times 10 caret negative 19. Excel will understand that. And we can see, we can check on our calculator, but there we go. We've actually converted electron volts to joules. It's not as explicit as our conversion factor, but that's why it's good to write out explicitly beforehand. So let's see if I could, I don't think I can pull it back up. Does it have memory for it? No, it does not. So once I wiped it, it couldn't remember what I wrote. But that's what we got. How do I go through it? Click, drag, bring everything down. So now comes wavelength. Well, I'm in joules, which is going to be in units of energy. So if I'm kind of thinking ahead, I have my energy now. That's here. That's where I would use it in an equation. H happens to be what I'm solving for. So it's telling me if I know frequency, then I'd effectively be done. I just have to rearrange this equation. However, I only have is energy and no frequency right now. But I do know lambda nu is related, so we have our frequency, which I want, is directly related to the wavelength, is which I have through the constant, the speed of light. So speed of light is incredibly quick, which is 3.00 times 10 to the 8th meters per second. So we have our constant. So effectively, we have everything we need. We're just working on manipulating everything so that I can dump my frequency directly into this equation and then calculate for H. So what I'll need to do then is go down here. So you would have probably finished at this point filling in your wavelengths from the spectroscope, so part A. Like I said, I'm only going to do a couple of these, so you still have to do some stuff on your own, so there's some learning, it's not just direct copying. But I'll go on with blue and infrared, because that's what we have. So again, what we need to do is make sure we convert into meters, which would be our next step. Why do I need to convert into meters? Well, there's going to be a reason for that. If we go back to my lambda nu equals c, I need lambda to be in meters because frequency is going to be in per second. So when I multiply those, when I multiply those two units together, I do get the units for velocity, because velocity is a speed. So I have to have my lambda in my correct units to make sure this relationship holds. If I left it in nanometers, I'd be about, what is that, a trillion-fold off, because I'd be off by 10 to the 9th, because there's 10 to the 9th nanometers in 1 meter. Make sure I did that correctly, right, because we have millis, -3, micros, -6, and then nanos, -9. Yep, we're in good shape. So, let's set up an equation where we can take 495 nanometers and then convert that into meters, which is what we just said. We said there's a lot, so 10 to the 9th nanometers in 1 meter. And what I can see is my units cancel, I'm left with meters, and I'm in good shape. So effectively what I did in Excel was going to take the number that's here, and then just divide by 10 to the 9th, and then I would have a number here. So effectively that's what I want to do. Just as a quick reminder, you can also use other conversion factors. We could have said 595 nanometers times, in 1 nanometer, there's 10 to the negative 9th meters. That is also perfectly fine. It will give you the same exact number, and we'll still have our units cancel and have meters. Right? It all depends on how you want to go about remembering your conversion factors. I find it easier to remember there's a lot of small things in one big thing. That's the conversion factor I typically use. But you're more than welcome to stick with this. Alright, so now we have what we're setting up. I need to convert this number, and I said I was going to divide by 10 raised to the 9th. There we go. Almost done. Again, let's remind ourselves where we're going. I still need to get frequency, because lambda nu equals c, so nu equals c over lambda. I'm trying to eventually plug it into this equation. So if I dump that in, it'll be c over lambda. I can immediately see h is going to be equal to e h over c. Effectively, that's what my final equation is going to look like, because I measured E with the voltmeter, well, then a little bit of dimensional analysis, and then I've also measured lambda. So I'm in good shape to get to Planck's constant. So what I need to do now is convert that meters into frequency. So I have my 495 times 10 to the 9th, which would be 4.95 times 10 to the, if I'm going that direction. You know what, I'm not going to try to do math in my head, let's do it the easy way. I know I have 495 times 10 to the negative 9th meters. I need to multiply it by a frequency, by a frequency. That will get me to 3.00 times 10 to the 8th meters per second. So if I do the math out, it's going to be nu equals, and I'm just going to do the symbols because it's easier to see, c over lambda. So I can now dump that in. I know this number, that's right there. Lambda is right there. So that's going to be our next step. Divide the speed of light by my wavelength. So how do I do that? I have to type in the speed of light, so 3.00 times 10 raised to the 8th divided by my wavelength in meters. There we go. It's hard to get an intuitive sense right now if you've done this correctly, because if we take a look how big that number is. You're talking about 10 to the power of 14, which is huge. But if you think about how fast the speed of light is and how small a nanometer is, so if we're looking at one wave of, well, make a couple, of light, if this was the blue light, that's 495 nanometers apart. So it's very, very small. It's passing through a point moving at the speed of light. So you can imagine a lot of these crests will pass in 1 second. So having something enormous like 10 to the 14th as a frequency per second is totally fine. So let's take stock of where we are. We're almost to Planck's constant. So we know E equals h nu. Therefore, h equals E over nu. Do I have energy? Let's take a look. I do. Do I have frequency? I do. So I'm in good shape. I now can see that I can divide my energy, which again we said is over here, divided by here. So let's convert that into an Excel equation. So remember, we want to be dividing our energy, which is here. So I'll click on that cell, divided by my frequency, nu. We can do that for both. It restarts the countdown, so I don't know if you can see it or not, but it still says it's recording, so that's good. So I take my average, 6.09 times 10 to the negative 34th. That's all right. It's kind of close to Planck's constant. And actually, when you do more of these, it does average off pretty well to Planck's constant, which is on the order of magnitude of 6 times 10 to the negative 34th. My units, though, aren't up here. Oops, wrong tool. Aren't up here. So I need to take a look at what my units would be. So I had my joules. I have my per second. Let's double check. H equals E over nu. E is in joules. Nu is in per second. It looks weird, but it's the same thing as joules per second. And I usually put a dot between them to symbolize that they're being multiplied. It's nothing special. Sometimes you might see books use a hyphen. I just think that looks confusing. So, all right. So we have our units. So maybe we should change that up here. Let's change that to joule seconds. I don't know what tool it just brought up, why it's not pointing on my screen. That's really weird. Alright. I don't want to mess this up because it's been going on for 30 minutes, so I'm just going to continue what's going on here. I'm going to do it by hand. We're almost done anyways. Standard deviation, how would you do that? There's one last command we need to know. So in Excel, to tell it to do a command, would have to hit equal, and it's stdev. They'll give you a bunch of drop-downs with S and P and other things like that. We are just using the command stdev. Once that's open, you can highlight, in this case, all of your experimental data. Make sure you omit the average, because remember, that average already has all that information in there. It's artificially weighting it. So don't include the average in the standard deviation, at least in your calculations. All right, so I hope that was much more clear. Fuck, it stopped. Did it really stop recording? Excuse me if you, my language, if you can still hear that. I hope it didn't. All right. So if it did cut off, I will follow up on that. If it did not cut off, hopefully we're in good shape. So if you have any questions on that, please send me any emails. Office hours, things got a little bit messed up last week. Office hours will be back to normal this week. Everything should be back to normal this week. So keep in touch. Good luck. Let me do this. What is going on? I want it to stop. I don't want to draw. Come on, it was a half an hour if I just lost all that. Why can't I have a choice? It is still recording, so that's good.